Welcome to the Chapter 5, Part 4 video. We'll be looking at the fundamental theorem of algebra, the rational root theorem, and the conjugate root theorem, which help us solve for the fundamental theorem of algebra. So the fundamental theorem of algebra, or FTA, it's an important abbreviation to recognize. The fundamental theorem of algebra is that a polynomial of degree n has exactly n roots. So as long as we have a polynomial that is not constant, so a linear, quadratic, cubic, quartic, quintic, and so on, we'll have exactly the number of roots equal to its greatest exponent. Okay, some of those roots can be complex non-real roots. Some of those roots can be multiple or multiplicity, right? So we've looked at these concepts separately. We're going to pull them all together into now the fundamental theorem of algebra. So now we can say that the degree of the polynomial is equal to the number of roots. And we can also say that that's equal to the number of linear factors of that polynomial. We kind of looked at this last class where I can write linear polynomials for each root, and that multiplied together will give me the polynomial itself, okay? This is a little bit different. Before we were looking at x-intercepts as giving us roots, but now that we have complex numbers, non-real numbers that can be our roots, we can't graph those on the x-axis. So this is different than the number of x-intercepts now. And we kind of looked at that when we were looking at quadratic, and we came across that in the project for some of us, but now we're formally stating it. So let's take a look at 3 examples and see how those relate to this fundamental theorem of algebra. Our first example is x cubed equals 0. Well, I can see that x cubed is my only factor. And so we can say that x cubed equals 0 means that x equals 0 with a multiplicity of 3. Because x would equal 0, it's x times x times x equals 0. So x equals 0. X equals 0 and x equals 0. Okay, now this is 3 roots or 3 zeros, and they're all 3 real. So that means there are 0 non-real solutions. 3 roots is the same as saying 3 complex zeros. Okay, now since 3 of them are real, that also means 3 x-intercepts, they just all happen to be at the same place. So if we look at the graph of x cubed, it really crosses through the x-axis here 3 times. And that is what makes the graph of x cubed kind of narrow down and then before it continues on. It's not a straight line. It kind of does this narrowing down because it's passing through that x-intercept 3 times at the same place. Okay, let's look at our next example. In our next example, and I'll do it in a different color so that we can tell them apart, x squared plus 1 equals 0. I can't factor that because it's a sum of squares, but I can use the square root property. So x squared equals -1. Then x equals plus or minus the square root of -1, which we recognize as plus or minus I. So that means that we have 2 roots. We have plus and minus I, but none of them are real. That tells me that this graph will never cross the x-axis. This is 0 x-intercepts. If we graph x squared plus 1, we should recognize that as a parabola that has been shifted up 1 unit. So we can see that it will never cross the x-axis. Okay, and then our last example here, x cubed plus 1 equals 0. And this one is going to use a little bit more space, so I'm going to erase some of this here. X cubed plus 1 equals 0. I can factor. That is a sum of cubes. That was our new formula that we learned how to factor last video. So that gives us x plus 1 times x minus 1 times x plus 1 times 1 equals 0. That's the formula for sum of cubes. Then we can say x plus 1 equals 0. but x squared minus x plus 1 doesn't factor. Anytime we factor sum of cubes, if there's no GCF, that second factor can't factor anymore. We know we're going to need the quadratic formula to finish solving this. X equals -1. We know that that one is real. A is 1, B is -1, and C is 1. X is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. So that becomes a +1 plus or minus the square root of 1 minus 4 divided by 2. Well, that's 1 plus or minus the square root of -3 over 2. That tells me it's complex imaginary. This is going to become square root of 3i. So that's 1/2 plus or minus the square root of 3/2 I. So we have 1, 2, 3 roots, 3 roots, and one of them is real. So that means one x-intercept, but there are still 3 roots, but 2 of them are imaginary. Okay, so that's what the fundamental theorem of algebra says. It says sometimes they're all real, sometimes they're all imaginary, sometimes they're a combination of the two. But the number of roots is equal to the degree. Degree 3, 3 roots. Degree 2, 2 roots. Degree 3, 3 roots. So if we take the real ones and the complex ones together, they should add up to exactly the degree of our polynomial. Okay, so let's see if we can find all of the roots of this example. Now I'm looking at this, and this is a really long polynomial. But even though we can't factor out a GCF looking at this, what we can do is we can go back to our basics and try factoring by grouping. So I'm going to group this by 2's, 2, 2, 2, okay, and take GCFs. So my GCF of my first pair is x to the 4th, leaving me x minus 1. GCF of my second group is -3, leaving me x minus 1. GCF of my last pair is -4, leaving me x minus 1. That worked out nicely. I have an x minus 1 here that I can factor out of each of those. Factoring out an x minus 1, I'm left with x to the 4th minus, whoops, I left out, my GCF here was 3x squared. So 3x squared minus 4 equals 0. Can I factor out this right-hand factor here? I want two numbers that multiply to -4 and add to -3. That's going to be -4 and 1. So we have x minus 1 times x squared minus 4 times x squared plus 1 equals 0. I can recognize the middle one as a difference of squares. So that's x minus 1 times x plus 2 times x minus 2. It doesn't matter which one you put first, the plus or the minus, but x squared plus 1 does not factor any further because that is a sum of squares. So that tells me that x minus 1 is 0 or x is 1. X plus 2 is 0 or x is -2. X minus 2 is 0 or x is 2. And x squared plus 1 is 0 or x squared is -1. Then x is plus or minus the square root of -1, which is plus or minus I. So what are all of the roots? X equals 1, -2, 2, I, and -I, plus and minus I. There are 1, 2, 3, 4, 5 roots. 3 of them are real. So that means there should be 3 x-intercepts, but there are still 5 roots because 2 of them are complex. Okay. So let's look at, what if I can't factor? If you looked at that last polynomial and you thought, wow, I don't think I can factor this. Well, there are other ways to get to the same place. Okay, now when you can factor, that's going to be the easiest. But we have a theorem that says if you can't factor, or if it doesn't look like you can factor, then what you can do is you can look at factoring just the constant term when a is 1. So the formal theorem is a little bit complicated. It goes into a lot of variables with a's and p's and q's and subscripts. So I put an example. If I have any polynomial and I gave a quadratic polynomial with some really big coefficients, 21x squared plus 29x plus 10 equals 0, doesn't look like I would be able to factor that. Okay, maybe you could give it a shot, but you would have to factor 210 looking for a sum of 29. Is it possible? Potentially. Okay, but maybe we can't get there. So then what would we do? We would divide everything by 21 so that we get an a of 1. And then we take our constant term and look at the factors of the numerator divided by the factors of the denominator. So 10 factors 1 times 10 and 2 times 5. The factors of 10 are 1, 2, 5, and 10. 21 factors into 1 times 21. 2 does not go into 21. 3 times 7, and that's as far as we can go. No other factors of 21. So we put all of the factors of 10 in the numerator, all of the factors of 21 in the denominator, and we divide each of them. So I'm going to take 1, 2, 5, and 10, all divide them by 1. I'm going to take 1, 2, 5, and 10, divide them all by 3. 1, 2, 5, and 10, all divided by 7. 1, 2, 5, and 10, all divided by 21. So what we end up with is a list of 16 factors in this case. Sometimes when you're doing this, you'll end up with, for example, this is unrelated to this problem, but you could end up with a case that you end up with something like 8 halves, which reduces to 4, which may already be in your set, in which case you wouldn't list it twice, just like with normal set notation. Okay. So what does this tell us? This tells us that one of these 16 numbers could be a rational 0 of this polynomial. But how do I pick them? I don't want to have to test 16 of them. And we can use our technology, we can use our calculator to help us out. So let's look at how we can use our calculator for that. I picked a different polynomial so that we can have a little bit of practice with looking at this P over Q list again. So x to the 4th plus x cubed minus 7x squared minus 9x minus 18. Something that's nice here to note is that our a value is already 1. So really we're looking at 18 over 1. So what we need to do is look at all of the factors of 18. We have 1 times 18, 2 times 9, 3 times 6, 4 does not go into 18, 5 does not go into 18, and then we're back around to 6. So this is my complete list of factors. That means my possible rational zeros are 1 over 1, which is 1, 2 over 1, which is 2, 3 over 1, 6 over 1, 9 over 1, or 18 over 1. So there's only 6 to choose from here, but that's still too many to test. So what we do is we graph that function into our calculator and we look at where does it cross the x-axis. So if we graph this in our calculator using the y equals function on your grapher, type in the function, make sure your exponents are in the exponents and the rest of it is not. Sometimes we accidentally type the whole thing into the exponent if we don't remember to click out of it. So, and what I mean by that is x to the 4th plus x to the 3rd minus 7x squared minus 9x minus 18. If it looks something like this, that means you kept typing in the exponent instead of x to the 4th. Click out of the exponent, click that right arrow so that the plus x is on the same level as the original x. Okay, if you need help specifically typing the function into your calculator, please set up office hours so we can go through that together. And then you hit graph, and what you'll see in standard view, which is zoom option 6, we can see that this crosses the axis at 3 and -3. Now that is in our list. 3 is in our list. Okay. So what we need to do now is we need to test if 3 is a 0. And the way we do that is with synthetic division. Now we looked at synthetic division in the last lesson. I'm going to review it pretty quickly here. So if I want to test x equals 3, I'm going to put 3 in the upper corner. And then I'll put the coefficients of my polynomial in descending order, making sure if I need any zeros. So I have x to the 4th, x to the 3rd, x squared, x to the 1st, and no x. I don't need any zeros here. Line underneath and a remainder box. The first number just drops right down. And then I do times 3, add those, times 3, add those, times 3, add those, times 3, add those. If my remainder is 0, that means it factored out perfectly. And if x equaled 3, that gave me a factor of x minus 3, which means f of x equals x minus 3 times my quotient. Now I started out with an x to the 4th, so my quotient is an x to the 3rd. So that's x to the 3rd plus 4x squared plus 5x plus 6. Now I still have a polynomial here that I need to continue factoring if I need to find the rest of the zeros. But notice here, x looks like it equals -3 as well. So let's try factoring out a -3. But instead of going back to our original polynomial, we're going to factor this out of the remaining polynomial, the quotient that we were left with. So there's a little bit of a shortcut that we can use here. If you're doing this in your notebook and you want to save space in the future, what you can do is you can kind of tag it on right here and say, okay, let me divide here by -3. Now I wrote my f of x underneath it, so I don't have space to do that this time. So I'm going to rewrite just underneath here, -3, 1, 4, 5, 6, line, and a box for my remainder. Bring down the 1 times -3, add them together, times -3, add them together, times -3, add them together. This confirms that x equals -3 is a factor, or is a 0 rather. So add 3 to both sides, x plus 3 is a factor. So now I know that f of x equals x minus 3 times x plus 3 times the quotient. So if this was, we started with x to the 4th, we factored out a linear term, a linear factor. So this left us with an x cubed, then this is x squared. X squared plus x plus 2. Okay, so I have 2 zeros so far, positive and -3. I'm going to take this last one, which is quadratic, and see if I can factor it. Do I have two numbers that multiply to 2 and add to 1? Well, the only numbers that multiply to 2 are 1 times 2, and those don't add to 1, so this does not work. Not factorable. So we'll use the quadratic formula. A is 1, B is 1, C is 2. X is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. -1 plus or minus the square root of 1 minus 8 divided by 2. -1 plus or minus the square root of -7 all over 2. This is going to become square root of 7i. So this is -1/2 plus or minus the square root of 7/2 I. Okay, so my final answer, I have that x equals 3, -3, -1/2 plus the square root of 7/2 I, and -1/2 minus the square root of 7/2 I. Degree 4, 4 roots or zeros. 2 of those are real, 2 of them are complex, non-real, or imaginary. Okay. If you've noticed a pattern, every time we have an imaginary answer, we always have them in pairs. They always come in twos. And there's actually a theorem that tells us that that will always happen. And the reason that happens actually comes from the same way we found the quadratic formula. So if you remember, in order to find the quadratic formula, we started out with just a generic quadratic equation, ax squared plus bx plus c. And then we used completing the square and solved for x in order to find the quadratic formula. And because of that, when we did the square root property in that process, we ended up with this plus or minus. And that tells me every time I solve the quadratic formula, I'm going to get 2 answers. Now, occasionally we have plus or minus the square root of 0. And remember, that's when we had a real solution, a real and rational solution. And that means that rational solutions are the only type of solutions that can be non-paired. Any other type of solution will have a pair. So that means if I have a square root of 5, automatically that answer will also come with a negative square root of 5. If my answer is 2 plus the square root of 15, that means my answer will automatically come with a 2 minus the square root of 15. If my answer is 5 minus I, it must automatically come with an answer of 5 plus I. If my answer is 7I, it must automatically come with an answer of negative 7I. Because of that plus or minus in our quadratic formula, any answer that has a radical or a complex part, if it has an I, it must come with what's called its conjugate. Now, we've talked about conjugates before several times, including last class. And the way that we can always make sure we're putting our conjugate answers together is that if I have an I or a square root, I look at that as a plus or minus. Okay, so I had a 7I, I should have plus or minus 7I. 2 plus the square root of 15, it's plus or minus the square root of 15. 5 minus I, it should be plus or minus I. Square root of 5, plus or minus the square root of 5. Every time you get an answer that has an I or a radical, a square root, there should be a plus or minus. You should have 2 answers there. Okay, now notice if I turn those into factors, it's always going to be x minus the entire 0. So it's not the x that changes sign. It's always x minus. It's the square root that changes sign, plus or minus the square root. And I comes from a square root, so plus or minus I, but always x minus. Okay. If a has a negative value, let's say our answer here, x equals -3 plus I, then x would also equal -3 minus I. They always come together in pairs. This would be a case, because the 3 is negative, when I solve for x, it will be x plus 3 plus or minus I in my factors. Okay, now this represents 2 factors, which is kind of a weird way to write it. It should be x plus 3 plus I, x plus 3 minus I. Okay, so let's look at an example. A quartic polynomial, quartic means degree 4, has rational coefficients if the square root of 2 and 1 plus I Our roots, anytime I see a square root, I think plus or minus. Anytime I see an I think plus or minus. What are the two other roots? Well, I kind of already answered that by identifying where the plus or minus would be. So I have square root of 2, then I need negative square root of 2. I have 1 plus I, then I need a 1 minus I. So my two roots that were not listed, but I know must be part of my polynomial are negative square root of 2 and 1 minus I. These are the conjugates of the given zeros. Zeros and roots mean the same thing. Zeros is the same as roots. Okay. The second part of example 2, what is a third degree polynomial function, p of x, with rational coefficients, so that p of x equals 0 has roots at -4 and 2i. There's an I there. I need plus or minus 2i. Write p of x in standard form. So I know that x equals -4, x equals 2i, but x also equals -2i. So then x plus 4 is 0, x minus 2i is 0, x plus 2i is 0. P of x equals x plus 4 times x minus 2i times x plus 2i. This is linear factorization. Or the factorization when it doesn't say to simplify. But we want this in standard form. So the next step is to multiply the conjugates. Now it doesn't really matter what order we multiply this in, but it's going to be easier if I multiply my conjugates first because I know those middle terms will cancel out. So make it a little bit easier on yourself and pause for a second before distributing and see if there are any conjugates. So I have x plus 4 times x squared plus 2ix minus 2ix minus 4i squared. We did this example in class. The I squared is -1 and the middle terms cancel out. So we have x plus 4 times x squared plus 4. This would be the real factorization. But we have to keep going because we want it in standard form. So we have distributing again, x cubed plus 4x plus 4x squared plus 16. Now it's in polynomial form, but standard form, polynomial form. Standard form is also descending order, so that's x cubed plus 4x squared plus 4x plus 16. And phew, we finally did it. We got there. P of x. Okay, so we started out with the answers. We had to identify the third zero. Third degree, don't start distributing until you have all three zeros. With third degree, once we have all three zeros, we're distributing. Identify the conjugates first to make it easier, then keep distributing until you have no parentheses left, and you finally get to standard form when you write it in descending order. Okay, I have a try this for you. Go ahead and try this on your own. Make sure you're reading this carefully. It is a quartic. Quartic means degree 4 polynomial with roots 2 minus 3i, that's one root, 8, 2. You're missing one. You need to find your last root before you start distributing. After you put in your answer to Edpuzzle, I will show you the answer. Okay, so since it didn't specify what form, you could have left it as a linear factorization, but in case you kept going, I did too. We start out by identifying that the missing root is 2 plus 3i. Set each of those four roots equal to x. Set those equal to 0. put those into factored form, that's all you had to do. If you kept going and you multiplied out the i's, you should end up with the second boxed answer, which is the real factorization. And then if you kept going until it was standard form, because that's the last example we did, that's absolutely fine. You didn't have to do that, but it's good distribution practice, and you should end up with the standard form that's in the last box there. So the first box is all you had to do. I think if you were kind of following along with what we did in the last example, you probably ended up with the last box. Okay, go ahead and pause if you need a little bit more time to read through that, or if you wanted to try converting forms and turning it into the last one. If you want to do that, go ahead and pause now before I move on to the next slide. Okay, this is the practice. There are 5 problems here for you to try and then upload your work to Blackboard. You have your quiz coming up. The end of the chapter is coming up pretty quickly after the quiz. So if you have any questions, make sure to set up office hours and I will see you in class.